Hi everyone, hope you're all keeping well. It's now time for our next lesson, which today will be on nuclear radiation. Okay, a lot of people worry about nuclear radiation. It's not necessarily anything to worry about as long as you know how to keep yourself safe. So, learning intention to explore the different types of nuclear radiation and to define and calculate the activity of a radioactive source. So success criteria for today: I can define the three main types of nuclear radiation. I can describe methods of stopping these types of radiation. I can perform calculations involving the activity of a radioactive source. So, what are atoms? What are they made of? Those of you that have done chemistry may know a little bit about this already, but we'll go over this just in case there's anyone out there who hasn't. So this is an example of what an atom kind of looks like. The atom is made up of three parts. It's up to three parts. Sometimes you only get two of them, but more often than not there's all three of these parts in here. First of all, we've got the proton. Now the proton are these red coloured balls in the diagram here. So the protons have a positive charge. We have our neutrons, which are these blue coloured balls here in the diagram, and the neutrons have no charge, or they are neutral, hence where the name comes from. And of course we've got our electron, which are these black ones, which are orbiting the atom in the diagram shown here. So, how is the atom structured? Well, we have this positively charged, densely packed centre. So basically we have our neutrons and our protons, which are kind of tightly packed. They're in the centre of the atom, and they basically, you can't get anything between them. They're just so close together, they're all touching. There's no way to get anything in between them. However, the electrons orbit around about the outside, a little bit like a cloud, or a little bit like the way the planets orbit the sun in our solar system. So they're orbiting around about, and there's actually lots of empty space between where the electrons are and where the nucleus is. So there's lots and lots of empty space there. So actually, lots of the biggest part of an atom is actually made up of empty space. So, first of our three types of radiation that we're going to be wanting to look at today is the alpha particle. So the alpha particle is the biggest, or the largest I should say, of the three types of nuclear radiation, and particularly the three types of the particles. So alpha, which is also represented by this little funny symbol here, it looks almost like a funny A. Alpha is the first letter of the Greek alphabet. Now alpha particles are made from two protons and two neutrons, which is the same as a helium nucleus for those of you that do chemistry. And it looks a little bit like this one here. So it's a little bit like the atom that we showed in the previous page as well, in the previous slide. So we have two protons and two neutrons here. Alpha particles are the most harmful of the three types, three most common types of nuclear radiation that we're going to be looking at today. So they are the one that we need to be the most cautious with almost. However, they can be stopped by a sheet of paper or a few centimetres of air. So even just the distance that the camera is from me at the minute, if I had an alpha source there, the alpha particles more than likely wouldn't be able to make it to me right now, so I would be quite safe. So actually alpha particles aren't so bad because they can't travel very far in air. Second of our particles is the beta particle. Now the beta particle is the smallest of the particles that are emitted as nuclear radiation. The beta, the letter beta, represented by this funny B here, is the second letter of the Greek alphabet. And you probably see a theme going on here. Beta particles are basically just fast-moving electrons, but they're emitted. It's important to know that they're emitted from the nucleus of the atom. That's actually quite important for all these types of nuclear radiation. They're all emitted from the nucleus of the atom, and that's where the term nuclear radiation comes from. It's because it comes from the nucleus of the atom. This is an example here, just kind of keeping in line with the previous slide where we introduced the atom. We have an electron here, and that would be moving very fast, and that would be emitted from the nucleus of the atom, and that would be a beta particle. Beta particles are less harmful than alpha particles, you'll be pleased to hear. However, they can travel through air much more freely, and if we want to stop them, we need a few millimeters of aluminium or something similar. Our final type of nuclear radiation is the gamma ray. Now, we've already talked a lot about what gamma rays in the past. Gamma rays are the fastest form actually of nuclear radiation because they travel at the speed of light. Gamma, well, I'm sure you've guessed it already, represented by this kind of funny symbol, almost looks a bit like a Y. It is the third letter in the Greek alphabet. Gamma rays are a form of electromagnetic radiation, so they're rays rather than particles. Not like these little balls which are kind of getting thrown about the place, as waves which are travelling about the place when we're talking about gamma rays. Here is a little example up at the top, just to keep this in line with what you've seen in the other slides. A little electromagnetic wave. Obviously it has a very high frequency, as you'll remember from when we talked about the electromagnetic spectrum. However, that is the gamma ray. Now, gamma rays are also less harmful than alpha particles, you'll be pleased to know. However, because they are waves, they are much harder to stop. So we need a few centimetres of some kind of quite dense metal such as lead, or maybe several metres of concrete. Okay, so it takes a lot to stop gamma rays. However, they are probably the least harmful of the nuclear radiations. So I'm going to get you to take a wee copy of this, similar to the way we did last time. What I'll do is I'll run through this, and then I'll give you a chance to pause and you can take some notes from this page here. So here's a table. This just shows the type of radiation, the symbol, what it is or what it's made from, and what can stop it. Okay, so I'd like for you to copy out this table just now. Just fill in all these parts, these three types of radiation, the symbol, what they are, and what can stop them. So I'll give you a chance to pause that video now. And now that we're ready to continue, background radiation. Now, this is something you might be familiar with, you might not be, but actually we are surrounded by radiation from background sources all the time. We are constantly being irradiated by nuclear radiation. As I said earlier, some people worry about nuclear radiation, but it isn't necessarily anything to worry about as long as you know what you're doing, know what you're talking about. Well, as I've said now, we are being irradiated all the time by this background radiation, and it isn't anything to worry about in the slightest. So there's nuclear radiation around us at all times. It is not anything we need to worry about because the levels are low enough that it isn't harmful to us. There are different types, so we get some which are naturally occurring, we have some which are man-made sources. Both of these contribute to the background radiation that affects us. We need to take this into account. So if we were going to be doing any calculations involving nuclear radiation, we'd normally need to take this into account. Now, I'm going to be introducing an equation just shortly, and we'll not need to worry about background radiation when we're talking about when I introduce this equation. But it's just something to be aware of for the future. Normally we would need to take into account background radiation. So some examples of natural and man-made sources are shown in this table here. So we've got some natural sources. So natural sources include radon gas, which is released naturally from rocks, and cosmic rays, which just come from stars. Basically, stars are releasing nuclear radiation, and some of it makes it into the atmosphere, makes it through the atmosphere, and it irradiates us. And there are also things like, for instance, bananas, which have a very low amount of radioactivity. Again, nothing to worry about. Doesn't mean you shouldn't eat a banana. It's just a fact that they have a very low level of radioactivity. Some man-made sources. Well, the main man-made sources that we tend to hear about are fallout from different types of nuclear weapons testing, which doesn't tend to happen these days, thankfully, anymore. We've kind of learned from mistakes we made in the past. And accidents at nuclear power stations. Thankfully, there's not a huge amount of those, but there's two bigger nuclear accidents that have happened at power stations. The famous one being the Chernobyl disaster, which was in 1982, I believe. I think in 2012 there was also an accident in Japan and Fukushima in a nuclear power station, which was caused by, I believe, an earthquake and or a tidal wave. However, obviously these are kind of concerns for when we were looking at nuclear power and generating energy from nuclear radiation. However, it's not something we're going to concentrate on just now. We'll probably come back and talk about that maybe in the next lesson. So how can we detect nuclear radiation? Okay, obviously if nuclear radiation can be a problem, it's useful if we're going to be able to actually, find out if we are being irradiated. I'm going to show you two examples here just of detectors for nuclear radiation. First one here is probably the one that you may be familiar with from movies, or so you occasionally see these in movies. This is the Geiger-Müller tube and counter. So here we have the Geiger-Müller tube here, and this is connected up to this counter, which we can see in the background. And basically what happens is when the source releases some nuclear radiation and it goes into the tube, it causes a little spark, which causes a pulse to be sent all the way back to the counter. When that pulse is reaches the counter basically increases by 1. This is the type of radiation detector that you maybe see them walking around with at a scene of a disaster in a movie, and you hear lots of clicks. The clicks come from the Geiger counter, and the more clicks you're getting every second, the more nuclear decays there have been, the more particles, or the more alpha or beta particles, or the more gamma rays that are being detected. The other type, and this one's almost slightly more useful, depending on what you're looking to do with it. This is called a film badge. So you've got a special film that's sensitive to nuclear radiation, which we put inside the film badge here. So this badge here opens up and we put in the special film inside here. And what we've got in here is we have different types of shielding. So we've got bits here, you can see actually in this diagram here, there's one of these windows here will have absolutely nothing in it, so there's nothing shielding it here. One of them will have maybe a little bit of plastic in there, and then we can see different types of metal in here. So one of these will probably be aluminium, and there'll be a little bit of lead in there. And basically what this allows us to do is it allows us to tell just which type of radiation has been detected. So you'll know obviously that lead will stop the gamma rays. It's definitely going to stop beta and alpha, so that's not going to get past there. The aluminium should stop most of the beta, however it's not going to stop the gamma rays. The gamma rays will get through the aluminium. So if this bit of the film had been irradiated, then we would know that there were gamma rays being emitted. And of course, where there's a little bit of plastic here, the plastic would likely stop the alpha particles. So if this bit has been irradiated, we know that it could be beta or gamma that has been that has passed through. We'd need to look to one of these other shielded areas. And of course, where there is no window, then or where there's nothing covering that window, there's no shielding at all. If that's the only bit, or if that's the bit that's irradiated, and that's the only bit that's irradiated, then we know that it must have been alpha particles that the detector has been irradiated by. And these are quite often used maybe in nuclear power stations, for instance, so you can keep track on kind of what someone's exposure has been to different types of radiation. Very, very useful. So, activity. Now, the activity of a radioactive source basically tells us how many nuclear reactions are happening, or how many nuclear decays are undergoing in that nucleus every second. Okay, so it's how many nuclear decays that the atoms are undergoing every second. Okay, a little bit like frequency was the number of waves we're detecting every second. Activity is the number of nuclear decays that the atom is undergoing every second, or the atoms are undergoing every second. Activity is measured in this unit here called becquerels. Now, you don't need to worry, you don't need to remember how to spell that. All you need to know is this abbreviation here, which is a capital B, small q. And then of course that brings us to our equation here. This is our equation which we use if we want to calculate activity. So we have A here, which stands for activity, measured in becquerels. We have N, which stands for the number of decays. Now, number of decays is just a number. There aren't any units associated with it, so we don't need to worry about units there. And of course T here is still time, and that is measured in seconds. So let's have a quick look at a worked example. A radioactive source undergoes 47,000 nuclear decays in 75 seconds. Calculate the activity of the source. And I know there's going to be a number of you are going to want to jump straight in and plug in the equation, write that equation down, really just jump straight in to get the final answer. Remember, we're going to go through the due process, and undoubtedly one or two of you will have came to this conclusion as well. First thing we do is our shopping list. Remember, we do our shopping list. So what I'm going to do is I'm just going to highlight the important information that's given to us in the question. So here we have 47,000 nuclear decays. So let's highlight that information there. We have 75 seconds. That looks like it might be important, so we'll highlight that there. And then it's telling us here what to calculate the activity. So let's highlight that then. So let's extract this information. 47,000 nuclear decays, that's just the number of nuclear decays it's undergone. So that we can assign to N here. 75 seconds, well, I'm presuming we're all quite happy with seconds being a unit of time. So T is equal to 75 seconds. And of course, A is our activity. That's what we're looking to calculate. So we'll just put that in with a little question mark. Now, time to get our first mark. Let's write down our equation. So plug in our equation here. We write down our equation. Remember, most of the time you just need to copy this either from an equation sheet or the sheet in front of you sometimes. Just write down that equation. That gets you that first mark. We're going to substitute in our numbers. So where I see N, I just go to here. I see N. N was 47,000, so I just change N to 47,000. Where I see T, I just go here to here. I see T is 75, so I just change T to 75. So I've got 47,000 divided by 75. That's been made by substitution. I can give myself another mark. Brilliant. Remember, that's 2 out of 3, 67% of the mark that we've got now. I'm going to do the calculation, and we come out with an answer like this, 626.666, and that number kind of was recurring, so I've put in these wee dots there. Now, we need to round this off. If we just write down this as our final answer, we're going to lose marks, unfortunately, so we do need to round this off. So what I'm going to do is I'm going to round this off to 630 becquerels. Remember your units. I like to put an underline there as well, just to make sure that I remember that that's my final answer. Now, why have I done this to two significant figures? Well, let's go back to our question here. A radioactive source undergoes 47,000 nuclear decays. Now, 47,000, that's 1, 2, these are all zeros, so that's two significant figures. 75, well, we've got two numbers here again, so that's two significant figures again. So two significant figures there, two significant figures here. We give our final answer to two significant figures. And that's your final mark, remember, with your units. So let's just double check where we get those marks for. First mark for your equation with, for writing down your equation. Second mark there for substituting in the numbers into the correct place. Remember, don't do any rearrangements. If you need to rearrange the equation, wait until after this point to do it, because you want to get that 67% worth of marks, 2 out of 3, before you make any mistakes. Now, that's not to say you will make a mistake, but you want to make sure that you've gained as many marks as you possibly can before you give yourself a chance to make a mistake. Then we get the final answer rounded correctly and with the units for our final mark. So that's a worked example. I'm going to give you guys some practice now. So I want you to go to the question booklets. Now, these are the same question booklets that we've been using in class. So if you've got your paper copy there, you're more than welcome to use those. I will also put a copy on Google Classroom just in case you've misplaced yours or you can't find it. Just means you've got it nice and handy for you. What I'll also do is I'll pop up the answer booklet as well, so you can check your answers as you're going through. It's important that you check your answers as you're going through, because you need to be able to pick up if you're making mistakes, if you're not getting something right. And if you're not getting something right, that gives you then the opportunity to ask for help, and we can get you on the right path before you have basically kind of learned something that's maybe not quite 100% right. So your practice, you're going to go to page 32 in the booklet, try question 1, 3, 5 and 7. Then you're going to turn to page 33 and do questions 1 to 5, okay? Now, there might be a little bit of rearrangement required in here. If I'm feeling generous, I might give you the equations on Google Classroom rearranged. But we're getting to a stage now where you're really going to need to be able to start thinking about rearranging equations, particularly if you're wanting to be doing National 5 next year when you're in S4. Okay, so I'll have a think about that one. Remember, check your answers as you're going through. The answer booklet is right beside the question booklet in Google Classroom. Separate from this assignment, I've put it separate so that you can refer back to it and you can find it easily at all times. If you're struggling, post a comment. You can post it either publicly or you can post a private comment in the assignment. I'll be watching the comments while we are in class, or while we're during class time, and I'll try and get back to you as quick as we can. Sometimes that might be in the form of a little picture, which just helps to answer a question. Sometimes it might just be a wee comment. I may even make a little video, but that takes a little bit longer, so I'm less likely to do that, to make a video response. If you do a private comment or you want to send an email instead, don't worry, I'll not identify you individually. I will just address any comments either directly to you, or if I'm making if I'm answering your question publicly, I'll not indicate that it was you that asked the question if you've asked it privately, just in case you don't like to ask these things publicly. So once you've done that, come back and have a look at our success criteria again. Our success criteria, I can define the 3 main types of nuclear radiation. I can describe methods of stopping these types of nuclear radiation. And I can perform calculations involving the activity of a radioactive source. Hopefully you can do all that. Hopefully you managed to get the questions right. If you have, give yourself a pat on the back. If not, go back and watch the video again or post a comment, ask for help. I'm more than happy to give you as much help as I possibly can. As I say, I'll be on here keeping an eye on these comments. If you do happen to kind of post a comment afterwards, I will try and keep an eye on it afterwards as well. I might not be quite as quick coming back to you afterwards as I will be if you kind of post it during class time. However, that's just something to be aware of. In the meantime, keep yourself safe and hopefully we'll get to see each other soon.